So today we're going to talk about using rates to explore how much change occurs over time. In the famous story, Alice in Wonderland, she eats treats that drastically change her height. So this website will be on the PDF of your notes. If you want to go back and look at it again, we can. But let's say we want to determine how much Alice has grown, but we don't have a measuring stick to directly measure her height. However, we do know the rate. Alice is growing at different times after she eats the cake. So at time 0, she hasn't grown yet because she hasn't eaten the cake. At 1 second, she's grown 1 foot per second. And I want to make sure that the most important thing that we can do in today's lesson is really pay careful attention to our units. After 2 seconds, she's grown 4 feet per second. After 3.5 seconds, 12.25 feet per second. After 4 seconds, 16 feet per second. So what I would like you and your partners to do is using the information in the table to determine how much her height has changed after each second. So talk it out with your group mates. Go. All right, so come back for just 1 minute as a check-in. The way that the question's phrased might be a little confusing, so let me provide a little clarification. After each second, you're like, well, that's what it is. But what we really care about is if we're looking for how much her height changes, we want to talk about between the intervals. So now that I talk about between each of the intervals that we have, does that change how you're going to find your calculations for how much her height has changed if we talk about where time is going to be between 1 and 2 seconds, where time is in between 0 and 1 second, where time is in between 2 and 3.5, and where time is in between 3.5 and 4. Go back and re-examine how that changes your thoughts. Change. So when we look at after 1 second, my change in my time, 0 minus 1 is 1, right? And then we have, she's grown 1 foot per second. So when we talk about this, her rate of growth is 1 foot per second, and that's happened for 1 second, which is why these seconds cancel out and you end up with 1 foot. So this is how much she's grown. So here where we're talking about how much her height has changed, we're working our way backwards from a rate table to a position table. So when we go back, we're removing our rate units, and we're going back to she's grown 1 foot in that 1 second. Okay, so then when we talk about the change in our next interval, the change in our next interval is our change in seconds. 1 more seconds happened. Now her rate here, there's nothing to subtract because her rate is now, she's growing at 4 feet per second. Remember, that's her rate of change. So now I want to go backwards and be like, okay, well, how many feet was that? So on this interval, just for this 1 second, she was growing at 4 feet per second. So that 4 feet per second, when I multiply, if I have 4 feet per second times that 1 second that I'm measuring, That's how I go ahead and I get this 4 feet, because these seconds cancel out. So her 1 foot she grew here, and her 4 feet she grew here. She's now at a total of 5 feet tall. Because remember, we're going backwards from our rate to our position. So we're canceling out our unit rates. So let's talk about what's happening here. Now we're talking about what's happening from 2 to 3.5 seconds. So now I've got 1.5 seconds is my change in time. She now is growing at a rate of 12.25 feet per second. And if it's easier for you to figure out if you want to write that second down here, because it's feet per second, she's growing at this rate for this many seconds. So you know how we talk about distance is equal to rate times time? Anytime you're multiplying your rate for how long it's happening, that's giving you your distance. In this interpretation, it's her height, how tall Alice is.
But it's asking how much she changed. So like she got to 4 feet, but she didn't, it was 1 plus 3 feet is how much she got to 3 feet, just the difference between.
Except for that wasn't her height. And so what we need to recognize is this is her rate of change. This wasn't how tall she was. So that's what we're doing right now, is figuring out how tall she was. After the first second, she was 1 foot tall. Then she started to grow at a rate of 4 feet per second. So after that next second, she grew 4 more feet, which means now she's 5 feet tall. Because what we're given in this table, is not her height. What we're given in this table is her rate. So that's like if you're driving your car and you're going 30 miles an hour for that 15-second interval, and then you speed up super fast because you got on 28 and you're going 60 miles an hour, your rate increased by 30. But that doesn't mean that your distance did. So we still have to go back and use this rate times time to figure out what our distance is. How far you drove, how tall she is. Does that help a little bit? All right, so let's talk about this one. So my change in my seconds is 1.5 seconds. And in that time, her rate increases to 12.25 feet per second. So meaning she's now grown in that 1.5 second this many feet. So if I want to know how much she's grown total, I have to say, okay, well, she started off at that 1 foot, and then she grew 4 feet. And then in this super phase, she grew 18.375 feet. So if you ask me how tall is Alice at that minute, her total height is going to be 23.375 feet. So let's go back and do this one together. Our change in time, our change in seconds, from 4 to 3.5 feet, or from 4 to 3.5 seconds, that's half a second. During that half a second, she grew 16 feet. So 16 feet per second is her rate. She only had half a second of growing at that rate. And that's how I know that when we look at how much she grew during that time, She grew 8 feet during that half of a second. So if I go back to my calculator and add her 8 feet, her total height at this point is 31.375 feet. So do me a favor, talk about this data with your group and answer problem number 2. Talk it out, go. In the problem above, you used Alice's rate of growth at different times to determine how much her height changed. Using words, summarize the mathematical process you did above. So you first looked at the change in the time for each interval. And then you went ahead and you multiplied that by the rate per second, and that's what gave you her total height for each interval. Now get back to what we talked about, where we talked about what we're studying this unit. The accumulation of change is going to be the sum of all of these heights. And that gives us her total height. So I figured out what is the time in just that one interval. I multiplied it by that time, by that rate of change. And notice my seconds, if I have a rate of change of 4 feet per second times 1 second, that tells me how many feet. That whole distance is rate times time. That rate times time gives me my total distance traveled. So that is her total height for each of these intervals. When I added them all up together, that is what we call the accumulation of change. Sound okay? Clear as mud. Let's look at this graph on the back. Okay. We can connect the process that we did in question 1 with a graphical representation. So you're going to fill in the table by describing what each part of the graph represents. So if I look at my x-axis, if I look at my input and come back to this chart, what is it that my x-axis or my input is represented by? Yeah, so your x-axis is going to be time. In what? That's going to be your time in seconds. So when you look at what your y-axis, that's going to be what it is that we're measuring. Your y-axis is always, what are you measuring? What is your output? So go back to your table and ask yourself, what is it that I'm measuring? Am I measuring height? No, I'm measuring the rate of her growth. So my output is the rate of growth. What is the units? How fast is she growing in feet per second? So when we talk about the horizontal line between 1 and 2, that horizontal line between 1 and 2, What do you think that that represents? That horizontal line between 1 and 2. Yeah. Horizontal line between 1 and 2. And for this, our horizontal line between 1 and 2 is going to be 1 second per second. What do you think about this vertical line at x is equal to 2? What does it measure? How tall is it? What number do you see here? What was that for? That's the rate of growth when? Rate of growth when? At 2 seconds. So if you look at our graph, you can see here is 0, 0. She's not growing. She didn't eat the cake yet. Here's 1, 1. She's growing at a rate of 1 foot per second. Now she's growing at 4 feet per second. Remember, this is the graph of my rate of change. This is the graph of your rate of change. So don't look at that as her being 4 feet tall. She's growing at a rate of 4 feet tall. She's not growing at all. She's growing at 1 foot per second, at 4 feet per second. At 3, isn't she growing at 9 feet per second? At 3.5, what was it, 12.25 feet per second? So this is the graph of our derivative. This is the graph of the rate of change. So here's an interesting conversation. Area of the rectangle. What rectangle are we talking about? What is the area of that rectangle? Yeah, that's her accumulation change. That's her height that she changed. She changed 4 feet. And the interesting thing is when we look at that, that's the amount of change in her height. So if you look at it, it's 1 second times 4 feet per second, and that's how you get 4 feet. That is how much she changed in that 1 second. Now I got to tell you something. Check this part out. When we look at this, and we look at this rectangle, that is how much she changed during that first section. What's 1 times 1? So far, her accumulation of change is her 5 feet. We're taking the derivative graph, and we're working backwards to try to figure out what it represented before we were looking at its rate. So that's the amount of change in height, and that is during that interval. We're going to start looking at curves of derivatives, and we're going to try to estimate how much change happened during those time intervals at that rate. Think about your speed graphs. I want to know how far Ricardo drove, what his change in position was, what his distance was. I'm looking at his rate. I'm looking at the time. So I'm going to start trying to figure out how much driving happened underneath this rate, because that accumulation of change should end up, when he does the tallying, should be equal to what his odometer told him was the distance that he covered. All right, so does this, anybody upset with me when I tell you this is her first second interval representing that, and this is her second interval? Anybody upset with this being a representation of that space under the curve? So what's interesting is there's some extra space that's not accounted for. If this here represents our accumulation of change and this area under the curve, we've got these extra things hanging out. So we go back to the understanding that this is just an estimate. So does it give us a perfect measure of Alice's change in height? No, because when we look at this curve, if I were to look at this curve, when I estimate the accumulation of area underneath the curve, notice I have parts under the curve and parts above the curve. So as I look at each rectangle that I have here, when I go to find what each rectangle represents, theoretically, the only part that has to do with what I care about is the stuff that's under the curve. And we can see that that curve cuts right through each of my rectangles. If I consider each of those rectangles, my estimation of her growth is going to be on the plus side. It's going to be an overestimation because I'm including these areas that are above the curve. But we can go ahead and we can say that if we estimate between 0 and 1, when I have 1 times 1, I get 1. Between 0 or between 1 and 2, I have 1 times 1, 2, 3, 4. And I recognize there's 4. When I talk about between 2 and 3.5, I'm up to, what was that, 12.25? And what did that end up being? 18.375. And when I talk about between 3.75 and 4, that half of an interval times 16 feet per second is equal to my 8 feet. So each of these rectangles, and I want you to pay careful attention because this is time in seconds and this is feet per second. So if I have 1 second times her rate of change, which is feet per second. I shouldn't be surprised that I have feet. And that takes me back to my original graph of what I'm looking at how tall is she? 1 plus 4 plus 18.375 plus 8 gave me a total of 31.375 feet that she grew. Take a minute, turn to your group, explain the colors, the boxes, the curves, the calculations. Go. Here's what we were going for. As time passes, her rate of change is increasing. She took the medicine or the cake, the poison, whatever you want to call it, and she grew faster and faster and faster and faster and faster. She was not growing at a constant rate of change. If she was, this would be linear. If she was growing at a constant rate of change, this would be linear. She's growing at an exponential model. Because as time passes, her rate of change continues to grow. When we look at what it is we're calculating, I know distance equals rate times time. Here's my rate, here's my time. I'm finding the area of all these little rectangles. Distance equals rate times time. That rate times that time gives me my distance. That's what I want to know. You're going to calculate how far your car drove. We just calculated how much Alice grew. So taking a look at today's notes, it introduces our next concept, which is I can use rates to explore how much change happens over time. And what we begin to talk about is the area under a curve, but an important conversation is what do we mean by the area under the curve? Because you'll hear lots of people talk about, when we talk about the derivative as a rate of change, we need to make sure people know it's not the average rate of change, it's the instantaneous rate of change. So somebody who thinks that they know what it is might not be specific enough. When we talk about the area under the curve, what I really mean is the region between the function and the x-axis. So when I'm talking about this area here under the curve, we have to know that we're stopping that measure at our x-axis. The important conversation here is when we talk about the area under the curve, we're actually talking about this area that's between the curve and the x-axis. So if you remember from pre-calculus, when you were measuring angle measures, they always had to come from the x-axis. Think back to that idea. I'm talking about the distance from my x-axis. So if I'm talking about, think about your x-axis as where 0 is. If I want to know the area under that curve, I'm talking about where does that curve, how much space exists between the curve and 0. Think about how much space exists between 0 and the curve. So when I'm talking about a curve that fluctuates above and below my x-axis, I'm talking about everything above, between the curve, and everything under. So that area under the curve is going to represent our total accumulation of change. If we're above the x-axis, that means that change is positive. If we're below the x-axis, that means that change is negative. So we want to be careful when we talk about area under the curve, making sure that we know we're actually talking about that space between the curve and the x-axis in both the positive and negative direction. All right, example 1. You are on a road trip. You have your car on cruise control. You're traveling at 60 miles per hour. How far have you traveled in 4 hours? If I know that distance is equal to rate times time, I know that my distance is equal to 60 miles per hour times 4 hours. And this is where we can look at those units canceling out. And I know that I have traveled 240 miles. So here's what's really cool. We can represent this by looking at our graph. Here is our rate of change. Here is our 60 miles per hour. And here is our 4 hours. So when we look at the 4-hour boundary, whoops, here's our 4-hour boundary, not this guy. 60 miles an hour for 4 hours. 4 hours times our area model that has us multiplying length times width has us going at 4 hours times 60 miles per hour. And that represents this whole area underneath our curve. Here's the Math 7 honors. Here's the calculus. Your accumulation of your miles is equal to the number of hours that you drove times your miles per hour. And you can see how they cancel. Your area under your curve is your length times width, and that's where you get your 240 miles. All right, let's look at example 2. The graph below shows the rate that water is leaking out of a tank. So here is my gallons per minute, and here is my minutes. So if my area is equal to my length times width, we don't have as pretty of a scenario here. But when we talk about how much water is leaking out of the tank, we're looking for our accumulation of the water leaking. How much water has leaked? When we multiply these units together, if I take my gallons per minute and I multiply it by my minutes, notice what unit am I going to end up with. So it's an exercise in finding the area under the curve. So in Math 7 Honors, they taught you how to do what they called composite figures, which is dividing up a graph into what you do know how to find the area of. So with your group mates, go ahead and see if you can figure out how much water is leaking out of my tank. Go. Do we agree? No?
Yes.
So for my rectangle, 2 times 6 is 12. For my circle, it's a semicircle. So it's 1/2 of pi r squared. The radius is 2. 1/2 of 4 is 2, so we'll leave it in 2 pi. Go ahead and leave it in pi if you can. For my rectangle, 1/2 base times height. So my base, I have my base as 1, 2, 3. Did you have your base as 3? Your height is 2. So that's going to be 3. So what's interesting is once I determine what my units are, I can go ahead and just do my math and make sure I attach my correct units onto that at the end. Alright, so we'll go ahead and talk about example 3. The graph below shows the rate of change for the number of people in a museum after it opens. So here's an interesting conversation. Take a look carefully at your units. This is how much time has gone by, hours, and here is my rate of people per hour. If I find the area under the curve, in a positive sense, if I have 100 people per hour in my museum for the first 1, 2, 3, 4 hours, I have 400 people in the museum. Make sense? If I have here, when I figure this out, my rate of people drops over that 1 hour and go to 0. But I can still figure out the area of this triangle because I can look at, okay, at a half hour's distance, I have 50 people. What's happening here? People are leaving because notice I go down into the negatives. So this is a weird concept of negative area because that represents the people that are leaving the museum. So at 8 hours after the museum opens, I have people leaving at a rate of 100 people per hour. I guess at the end of the day, what I want to do is make sure that the same number of people that came in walked out. Remember that from the Mixed Up Files of Mrs. Basil Frankweiler? Remember that book when you were little? About the 2 kids that stayed in the museum?
No.
All right, tackle this problem with your friends. Go. All right, so the way I have it is we need to go find the 100 people that haven't left yet and get them out after the museum's been open.
Not in the museum?
That was one guy.
So 400 people came in, 450 people came in, 350 people left, so there's 100 people left in the museum. Hey, when we're looking for our units for that area under the curve, that's going to represent the product of your x and y units. Knowing that, go ahead and look down at example 4. Each function listed represents a rate of change. What are the units for the accumulation of change? Talk about it with your friends. Go. So for the homework, a tank is filling up with water at a constant rate of 4 gallons per minute. That's this one like we did here. This is at a constant rate.
Yeah.
So after a half of a minute, if I have 4 gallons per 1 minute, and I have a half of a minute, what is that going to give me? Say it out loud. Yeah. Oh, did I miss you? I'm sorry. Sorry, I'm not throwing away. Don't be looking. All right, after 2 minutes, what do I have? Since it's a constant rate, do I need to adjust my values like I had to do for Alice? So compare the curve that I had for Alice, where I had to find each of my rectangles individually. Because this is filling up at a constant rate, do I need to change my intervals? Food for thought.